Previous example, we looked a little bit at how you can see the difference between what a device is doing based on the power consumption. And what we're going to do now is we're actually going to look a little bit more than just seeing what a device is doing. We're going to look at how we can see what a device is processing in terms of data. And so it's a subtle difference, right? Before we were looking at changes in the program flow, now we're going to be looking at the same exact program flow but different data. And why this works, so we didn't talk about where those power differences came from in detail before, but basically when you look at a microcontroller, you have internal data buses on it. So those data buses are going to interconnect, right? So on the left side here, we have a block diagram like from a data sheet. And you can see, for example, right, you have like a, what can we see here? We have some memory, right? Somewhere there's going to be like the processor core itself, which would have your like instruction decoding and all that stuff, right? But we also have peripherals and everything. And what interconnects it? Well, we have some big processor bus. This big processor bus, if physically on the chip, is going to, interconnect a bunch of different areas. So some of these regular structures, and I can't really see what's what here, might be like flash memory or something. The logic for this stuff is going to be somewhere in this, in these gates here, and there's going to be some interconnect. So we can imagine, right, that we basically have what's effectively wires on this chip. So it's, it's very much like what you expect. Like you have different areas of the chip and wires interconnect them. And what do we do to drive this? Well, to drive this bus, because this bus is actually kind of a pretty big capacitive load. And so we have typically like some gates that are actually driving the bus. And those gates that are driving the bus are designed to be fairly strong drivers. And this is just fundamentally because we have this kind of, relatively long load, large load, and that large load is because we have a bit of capacitance to the bus and stuff like that. So we need a fairly powerful drive. To do this, so if we imagine our data bus, right, is basically like a capacitor here, right, because it's effectively a line over top of a ground plane. It's basically a capacitor, right? We're going to be charging or discharging this capacitor. And so if we take the capacitor from 0 volts to 1 volt, it takes a different amount of energy than if we take the if we don't change the voltage at all, if we go from 2.5 to 5 volts or something like that. So what's kind of cool is that if we imagine our data bus here, and let's just imagine, say, 3 bits, so this is bit 0, 1, 2, right? And if you take your data bus and let's drive all these lines high at once, we actually see, if you were to like graph the power usage, right, you'd actually see a big spike at the moment in time all those lines get driven high at once. And so it actually takes an amount of power to drive the data bus. And we could even see it if we just drive, so if we go down to just a single line, right, we'll still see a little blip. It won't be as pronounced. But we'll still see a blip at that point in time when it switches from 0 to 1. This is a tiny, tiny, tiny signature. So, it's hard to just observe it directly. But what we're going to look at is how power analysis can actually be used to detect that. So before we get into how power analysis works to detect this, what we're going to look at first is why we might want that, and in particular, why knowing a single bit of data is going to allow us to break cryptographic algorithms and recover information out of them. Where we're going to see this data-dependent power from, right, is a few things. So I had sort of talked about the charging and discharging of the bus. The other thing you notice back here is that there's actually these 2 transistors, and if they don't switch perfectly, there's going to be a moment in time when they have what they call the shoot-through current, which is when both of them, to some degree, are on. So you have some extra current flowing that way, right? So we have all these various sources that are giving us this blip, basically. This blip indicates we have some power consumption that depends on the state of the bus itself. So we'll look at how to exploit that in a very general sense first, and then we'll look at what that means for actually power analysis next.